Hey there, science fans! Today, we're diving into the exciting world of electronics with the RLC circuit. This little circuit packs a punch, forming the backbone of many technologies we use every day. From radios to filters, the RLC circuit is a true marvel of electrical engineering. So what exactly is an RLC circuit? Imagine a small loop of wire with three key components connected: a resistor, R, an inductor, L, and a capacitor, C. These components work together in a fascinating dance of electrical energy, creating a variety of useful effects. RLC circuits are like tiny orchestras of electricity, with each component playing a unique role in shaping the flow of current. By understanding how these components interact, we can unlock the secrets of this versatile circuit and appreciate its impact on our technological world. Get ready for an electrifying adventure as we explore the ins and outs of the amazing RLC circuit. First up, let's meet the resistor. This component is like the chaperone of the RLC circuit, always keeping the energy in check. Resistors are designed to resist the flow of electrical current, converting some of that energy into heat. Think of it like a hose with a nozzle. The narrower the nozzle, the harder it is for water to flow through. Similarly, a higher resistance means the electrical current has a tougher time passing through, leading to less current flow. Resistors are essential in RLC circuits because they help control the rate at which energy is stored and released by the other components. By adjusting the resistance, we can fine-tune the circuit's behavior and make it work in specific ways. So, next time you crank up the volume on your radio or switch channels on your TV, remember the humble resistor, working behind the scenes to keep the electrical energy flowing smoothly. Next we have the inductor, the master of magnetism in our RLC circuit. This component is basically a coil of wire, often wrapped around a core of magnetic material. When electrical current flows through the inductor, it creates a magnetic field around the coil. Inductors are like the energy savers of the RLC circuit. They resist changes in current flow by storing energy in their magnetic field. When the current tries to increase, the inductor pushes back, trying to keep it steady. Conversely, when the current tries to decrease, the inductor releases its stored energy to keep it flowing. This property of inductors, known as inductance, plays a crucial role in filtering out unwanted frequencies and shaping the overall response of the RLC circuit. By carefully selecting the inductance value, we can tailor the circuit to specific applications like tuning into radio stations. So remember the inductor, the magnetic field magician that adds a touch of stability and frequency control to our RLC circuit. Last but not least, we have the capacitor, the electric field wizard of the RLC circuit. This component consists of two conductive plates separated by a non-conductive material called a dielectric. Capacitors store electrical energy in an electric field between their plates. Imagine a water balloon. As you fill it with water, the balloon expands and stores potential energy. Similarly, when you apply a voltage across a capacitor, it stores electrical energy in its electric field. When the voltage is removed, the capacitor releases its stored energy, like a discharging water balloon. Capacitors are excellent at blocking direct current, DC, while allowing alternating current, AC, to pass through. This property makes them invaluable in filtering circuits, where they can selectively remove unwanted frequencies from a signal. So, let's give it up for the capacitor, the electric field wizard that adds energy storage and frequency filtering to our RLC circuit. Now that we've met the stars of the RLC circuit, let's see how they work together in perfect harmony. One of the most fascinating phenomena in RLC circuits is resonance, where the circuit oscillates with maximum amplitude at a specific frequency. Think of pushing a child on a swing. If you push at the right rhythm, matching the swing's natural frequency, the swing will go higher and higher. Similarly, when an RLC circuit is driven by an alternating current at its resonant frequency, it experiences maximum energy transfer between the inductor and capacitor. At resonance, the reactance of the inductor and capacitor cancel each other out, leaving only the resistance to oppose the flow of current. This results in a sharp peak in the circuit's impedance at the resonant frequency, making it highly selective to that particular frequency. Resonance is a crucial concept in many applications of RLC circuits, from tuning radios to designing filters. By carefully selecting the values of R, L, and C, we can fine-tune the resonant frequency and create circuits that resonate at specific frequencies of interest. Section 6. Damping. Taming the Oscillations. While resonance is a powerful phenomenon, sometimes we need to tame the oscillations in an RLC circuit. This is where damping comes in. Damping refers to the loss of energy in an oscillating system, causing the amplitude of oscillations to decrease over time. Imagine a pendulum swinging back and forth. In an ideal world with no friction, the pendulum would swing forever. However, in reality, air resistance and friction at the pivot point cause the pendulum to gradually lose energy, eventually coming to a stop. In RLC circuits, damping is primarily caused by the resistor. As current flows through the resistor, some of the electrical energy is converted into heat, effectively dissipating energy from the circuit and reducing the amplitude of oscillations. The amount of damping in an RLC circuit can be controlled by adjusting the resistance. Higher resistance leads to greater damping, causing the oscillations to die out quickly. Conversely, lower resistance results in less damping, allowing the oscillations to persist for a longer duration. Section 7. Oscillations, the ups and downs of energy. One of the most captivating aspects of RLC circuits is their ability to oscillate, meaning the electrical energy swings back and forth between the inductor and capacitor. This continuous exchange of energy creates a rhythmic pattern of rising and falling voltage and current, much like a swinging pendulum. Imagine a basketball bouncing up and down. As the ball rises, its potential energy increases, and as it falls, its kinetic energy increases. Similarly, in an RLC circuit, the inductor stores energy in its magnetic field, while the capacitor stores energy in its electric field. The frequency of these oscillations, known as the natural frequency, depends on the values of inductance and capacitance in the circuit. Larger values of L and C result in lower frequencies, while smaller values lead to higher frequencies. These oscillations are what make RLC circuits so versatile and useful in various applications. By harnessing the power of oscillation, we can create circuits that filter specific frequencies, generate signals, and even store energy. Section 8. Real-world wonders, RLC circuits in action. RLC circuits are more than just theoretical concepts. They play a vital role in countless electronic devices we use every day. From tuning our radios to filtering signals in our smartphones, these circuits are the unsung heroes of the electronics world. One of the most well-known applications of RLC circuits is in radio receivers. By adjusting the capacitance of a variable capacitor, we can change the resonant frequency of the circuit to match the frequency of a particular radio station. This allows the receiver to pick up and amplify the desired signal while rejecting others. RLC circuits are also widely used in filters, which are essential components in audio equipment, telecommunications, and many other electronic systems. Filters use the frequency-selective properties of RLC circuits to allow certain frequencies to pass through while blocking others. For example, low-pass filters, commonly used in audio systems, allow low-frequency signals to pass through while attenuating high-frequency signals. This helps to create a cleaner sound by removing unwanted high-pitched noise. Section 9. Conclusion: the enduring power of RLC circuits. As we've explored in this electrifying journey, RLC circuits are more than just simple combinations of resistors, inductors, and capacitors. They are elegant examples of how basic electronic components can work together to achieve remarkable feats. From tuning our radios to filtering signals in our electronic devices, RLC circuits have shaped the technological landscape we live in today. Their ability to resonate at specific frequencies, oscillate with controlled damping, and store and release energy makes them indispensable in countless applications. As technology continues to advance, we can expect RLC circuits to remain essential building blocks for future innovations. Their versatility, efficiency, and enduring power ensure that these fascinating circuits will continue to shape the world of electronics for generations to come. So, next time you encounter an electronic device, take a moment to appreciate the ingenuity and elegance of RLC circuits, working tirelessly behind the scenes to power our modern world.